not so useful because we would call this as poor spatial mode matching. If we wanted to use it, we would somehow have to collect all of these, this emission that's happening, a standard scattering problem. The other thing is that, in fact, this atom is very small, and the scattering cross-section is small for natural atoms. But in the superconducting context, we're not in 3 dimensions. We're actually in a 1-dimensional waveguide. Here it's shown as a coax. The transverse directions are confined, and so basically photons can either go left or right. That's it. And so if we put in some energy from the left, it drives this transition. When it emits, there's really only 2 directions for the emission, to the left or to the right. And these 2 will quantum mechanically interfere if, on average, the photon number is much less than 1. They'll interfere such that the scattering is a reflection and it's perfect. And there's a destructive interference for the photon to go forward. I'll show some data in just a moment. But this is an advantage of the 1-dimensional waveguides we have. Now, for the experts, you may also be wondering about what constitutes strong coupling here. If we think of the cooperativity factor, there's a cavity enhancement times the electromagnetic field overlap. Now, here there's no cavity, so just imagine that that term is 1. But with superconducting qubits, because we can couple the qubit to the waveguide, say capacitively or inductively, we can basically design that to be arbitrarily large. And we can more than make up for the cooperativity using this factor, even though there's no cavity anymore. And so in this architecture, superconducting waveguide QED features 1D confinement and has very strong coupling, which means the rate at which we exchange energy with the waveguide is much higher than any non-radiative internal relaxation rate. Okay, so those are the definitions. Now, with a little more fidelity, we just looked at the 3 qubits coupled to a waveguide. The rate at which we exchange energy is gamma. The qubit frequency is omega. There can be some internal relaxation. And the way that we realize that is in the following way. We use a 50-ohm transmission line. There are qubits shown here, 3 of them. Now, the version that we're using here is a little bit more complicated than the, quote, hydrogen atom. This one, it has a squid, so rather than 1 junction, we have 2 junctions in parallel with a capacitor. So that's an inductor and a capacitor. But this inductor is tunable by a magnetic field. And so by tuning the inductance, we're tuning the resonance frequency of our qubit in situ, and that's very useful for this experiment. This is what it looks like if we're looking down on a chip that has this device. So the qubit is in the center, and in fact, this square is part of the capacitor. This is 1 plate. The other plate is ground. So rather than a parallel plate capacitor, we have a lateral capacitor. The squid is this small loop here. If we zoom in, you can see it. There are the 2 junctions, and we put in a magnetic field using an antenna. That's this antenna here. The qubit capacitively couples to this coplanar waveguide. That's shown here. And then we can drive transitions in the qubit with this drive line here, also capacitively coupled. Okay. So the first experiment is one that was done many years ago at NEC in superconducting qubits and in the 70s with natural atoms. This is resonance fluorescence in 1D. So if we have a qubit coupled to a waveguide, and this is all in the dilution refrigerator at millikelvin temperatures, the network analyzer is at room temperature, and we send out a tone out port 1. It goes down, follows the waveguide, interacts with the qubit, and then there's scattering that goes backwards and forwards. Now we can measure the forward scattering, and so we look at it with some amplification at port 2. So we remember that if we put in radiation and our average photon number, it's a low enough field that on average 1 or much less than 1 photon arrives at a time at the atom gets excited, it emits, and there's perfect constructive interference for the reflection. And that's exactly what we see. So if we look at the magnitude of S21 on this axis, so the amount of energy that gets to the second port, as a function of the probe detuning, so 0 is on resonance, we can see that when we're on resonance, the amount that goes forward is less than 1 part in 10,000. So basically, the destructive interference is almost perfect. But even detuning a few megahertz, now this qubit is at 5 gigahertz, even detuning a few megahertz, and you can see that that doesn't happen anymore. This is actually a slice taken on this dashed line here. This is the real and imaginary part of the S21, and you can see the enhancement there, or the suppression, I should say. We can also ask what happens if we increase the drive along this vertical axis. And so when we do that, we see that as long as we're in the 1 or much less than 1 photon on average limit, very little gets through. But when we turn up the amplitude, we see more and more power start to get through. And the intuition here is that while one photon is interacting with the atom, many other photons just rush by and go to port 2. Okay. So let me now talk about the experiment that we did. So the device geometry is as follows. We have 2 qubits, qubit A, qubit B, and they're coupled each at 2 points along this 50 ohm waveguide. And we choose to separate the points by a fixed amount, shown here. And if we look at the phase accrued between points, they're all equal. So they're equidistant, and that phase is related to the distance that we separated, physical distance, the velocity of light in this waveguide, which is about 1/3 the speed of light, and of course the frequency of the qubits, which we can tune with a magnetic field. Okay, this is what the, okay. I think I'll stand over here and do it this way. So this is what the device actually looks like. The qubits are in yellow. This is the capacitor. This is the capacitor of the 2 qubits. You can see it here, and the inductor is here. And the waveguide is in blue, and you can see that it goes between the qubits, back and forth, and over, and it couples to each qubit twice, just like we expected. It couples twice, okay? So the first experiment was to show that we can tune the dissipation to the waveguide. So for this experiment, we're going to detune qubit B. We'll put it at some other frequency where it's out of the experiment. And we only look at what happens to qubit A. Now, qubit A couples to this waveguide at 2 points, and the total round-trip distance, the way we've defined it, is twice phi. 1 phi to qubit B and 1 phi back. And if we put qubit A in its excited state and ask how does it relax, well, it actually can relax by emitting on either side. So of course it can emit to the left to this point x1 and go to this 50 ohm environment, or I should say it emits to the right and has this round trip, and then that goes to the output. And as you can see, this looks like an interferometer, and that's exactly what it is. And if we choose this phase properly, then we can either have destructive or constructive interference. Now, we want to suppress decay to the 50 ohm environment, so we tune the phase so that we get perfect destructive interference. And again, the way we can do that is by tuning the frequency of the qubit. Now, you might be wondering, what about the other 50 ohms? And that's certainly valid. But of course, those photons can either go to the left or to the right, but it's the same interferometer, and so there's the same destructive interference to both. So we showed that this works pretty well by looking at the T1 time, which is the exponential decay time of our qubit, when it's biased with different frequencies. And at this, what we call this decoherence-free frequency, this is the decay rate 1/T1, it's minimized at this particular frequency where the destructive interference is very, very good. And now the qubit's relaxation time, which is about 31 microseconds, is only limited by its internal dissipation. But loss to the 50 ohm environment has basically been eliminated. Now, if we detune the frequency, we're changing the phase, and we're making it more and more constructive, or less and less destructive, and so the decay rate increases. Okay, so we can tune the dissipation to the waveguide. Now, the second question is, can we now have the qubits interact with one another via the waveguide? And that's the same setup that we've seen here. And I'll say without justification that the coupling strength between these 2 qubits mediated by the waveguide is gamma over 2 times sine of this phase separation. And gamma is the decay rate, remember, at which it couples to the waveguide. And you see that there are 3 sections where qubit A is coupled to qubit B. And there's also a 4th section where the outermost points talk to each other, and of course that makes it now 3 times phi. This is a coherent process, and so the net coupling between these qubits is a sum of all of these coherent pathways by which they're connected. And we can show that this, in fact, works, that if we keep one qubit at a fixed frequency and we detune the other qubit, when they come on resonance, there's an exchange interaction which opens up an avoided cross